Module 6, Lecture A, Regression Metrics. By the end of this lecture, you will be able to describe common regression metrics in intuitive terms, compute simple regression metrics on small numeric examples, and interpret regression metric values in the context of the original problem scale. Summarizing prediction errors. Mean absolute error. Mean absolute error is a simple way to measure how far predictions are from the true values. Instead of averaging raw errors which can cancel out when some are too high and others too low, it uses the absolute size of each error. It then averages these absolute errors to show, on average, how much predictions differ from reality, regardless of direction. Mean absolute error is easy to interpret because it uses the same units as the values you are predicting. If you are estimating apartment rents and the mean absolute error is 500, your predictions are off by about $500 on average. If you are forecasting electricity demand and the error is 10, your predictions typically miss by about 10 megawatts. Because it stays on the original scale, mean absolute error helps you quickly judge whether that average error is acceptable or too large for your specific context. Mean absolute error measures how far, on average, your predictions are from the actual values, treating all errors the same. An error of 2 units counts as twice as large as an error of 1 unit, and an error of 10 units is 10 times as large, whether you predicted too high or too low. This makes it useful when you want to penalize overestimates and underestimates equally, such as when both shortages and surpluses in inventory are problematic. Overall, mean absolute error gives a simple, intuitive summary of how much your predictions are off from the truth. Squared error intuition. In regression, squared error measures how far our predictions are from the actual values while giving extra weight to larger mistakes. Instead of using the raw difference, we multiply that difference by itself, so small errors stay relatively small, but large errors become much bigger. This is useful in situations like predicting daily electricity usage, where being off by 1 unit is minor, but being off by 10 units is serious. Squaring the error captures the idea that big mistakes are more costly or risky than small ones. Squared error measures how consistent and reliable a model's predictions are by emphasizing larger mistakes. When a model makes many small errors, their squared values remain small, suggesting the model is generally accurate. But if it occasionally makes a large error, squaring that error makes it dominate the overall measure, signaling unreliability in those cases. For example, in predicting hospital wait times, small errors may be acceptable, but large errors become very influential once squared, drawing attention to serious problems for patient experience and resource planning. Squared error measures how far predictions are from true values by taking the distance between them and squaring it, which makes larger errors count much more than smaller ones. When we average these squared errors across many predictions, we capture both the typical size of the errors and how often very large mistakes occur. In financial forecasting, for example, a model that sometimes badly underestimates losses will produce extremely large squared errors on those days. This makes squared error especially useful for stakeholders who want to strongly penalize rare but severe mistakes. Penalizing large errors. When evaluating regression models, we need to look beyond the average error and pay special attention to large mistakes. In many real-world situations, a few big errors can be far more harmful than many small ones, even if the overall average error looks similar. For example, a small error in predicting a medication dose might be acceptable, but a large error could be dangerous. To address this, some evaluation metrics penalize large errors more heavily, so models that occasionally make extreme mistakes are scored worse than models that make smaller, more consistent errors. When we square errors before averaging them, Small errors shrink in importance, while large errors grow much more influential. This makes metrics based on squared errors especially sensitive to big mistakes. As a result, a model that occasionally makes very large errors will receive a worse score than a model that makes more consistent but smaller errors, even if their average error sizes are similar. Overall, squaring the errors favors models that avoid rare but severe failures. In high-stakes fields like finance and energy, it is especially important to reduce large prediction errors because a single big mistake can outweigh many small successes. In financial risk modeling, one major loss can cancel out many gains, so analysts use metrics that strongly penalize large errors to better reflect true risk. In energy forecasting, avoiding big errors helps prevent blackouts and waste. By choosing metrics that focus on large mistakes, analysts push models to avoid catastrophic outcomes and determine which models are suitable for real-world use. Hands-on regression metrics. Tiny data examples. To build a strong understanding of regression metrics, it helps to start with very small datasets that you can easily picture, such as predicting sales for a coffee cart over a few days. With just a few actual and predicted values, you can manually compare each pair and see exactly how the errors arise. This simple hands-on practice removes the distraction of large datasets and lets you focus on how each metric responds to the numbers. By calculating the metrics by hand, you develop an intuitive feel that will make it easier to work with larger, more complex datasets later on. Suppose you are predicting systolic blood pressure for a few patients, and you compare each actual reading with the model's prediction. By looking at how far off each prediction is and whether it is too high or too low, you can directly see the size and direction of the error. From these individual errors, you can compute metrics like the average error or the average squared error. This helps you understand how each prediction contributes to the overall performance measure instead of treating that final number as something mysterious. Working with very small data examples is a powerful way to compare different kinds of problems using the same simple structure. You might look at a few days of predicted electricity usage, house prices, or exam scores, each with a small set of actual and predicted values. This lets you clearly see patterns, such as how outliers change metrics, or how small shifts in predictions affect results. By practicing with these tiny datasets, you learn to connect raw numbers, calculated metrics, and their real-world meaning, which prepares you for analyzing more complex data and models. Metric calculations walkthrough. To understand regression metrics, imagine predicting daily energy use for several office buildings and comparing your predictions to the actual values. For each building, you line up the predicted and actual consumption and compute the error by subtracting the prediction from the actual value, keeping track of whether the error is positive or negative. These individual errors are then combined into summary measures that describe the model's average error, the typical size of its errors, and how strongly large mistakes influence the overall assessment of performance. In this way, raw prediction errors are turned into meaningful metrics that help you evaluate how well the regression model is working. To evaluate regression models, you can use several related error metrics. The mean error is the average of all prediction errors and shows whether the model tends to overpredict or underpredict overall, but positive and negative errors can cancel out. The mean absolute error avoids this by averaging the absolute size of the errors, giving the typical magnitude of prediction mistakes. To place more emphasis on large errors, you can instead square each error, average these squared values, and then take the square root, which makes the metric more sensitive to outliers. To judge how well your model performs, compare it to a simple baseline that always predicts the same value for every building, such as the average consumption. First, compute the total squared error of this naive baseline by summing the squared differences between the actual values and this constant prediction. Then, compute the total squared error for your model's predictions in the same way. By comparing these two errors, you can express your model's improvement as a proportion, which can be negative if the model is worse than the baseline, and up to 1 if it predicts the actual values perfectly. This gives you a clear sense of how much better your model is than a very simple approach, even on a small dataset. Python code metric calculations walkthrough. This script introduces basic regression metrics using small examples of energy consumption predictions. It focuses on clearly showing how each metric is calculated and what the resulting values look like. By walking through simple cases and printing the metric outputs, it helps you understand how to interpret regression performance in a straightforward way. The script explains that the necessary libraries are already available in a typical Colab environment, which is often used to run Python code. It notes that if the numerical library is not installed, there is a commented instruction showing how to add it. This setup ensures that the tools needed for numerical operations on arrays are ready. As a result, the script can efficiently perform calculations without additional configuration. We begin by importing the numerical computing library NumPy, which provides efficient tools for working with arrays of numbers. This library is essential for performing fast and convenient numerical operations. Throughout the script, it allows us to handle and manipulate numeric data in a reliable and efficient way. We begin by defining the daily energy use for 4 buildings, measured in kilowatt hours. These values are 10, 15, 20, and 25, with each number representing the consumption of one building. They are stored together in a numerical array, so we can easily perform calculations on them later in the analysis. We represent the model's predicted energy use for 4 buildings in a single array, with values of 12, 14, 18, and 30 kilowatt hours. These predicted values will later be compared with the actual energy consumption for each building. By examining how close the predictions are to the real values, we can evaluate how accurate the model is. Before calculating any metrics, we first check that the arrays of actual values and predicted values have the same length. This ensures that every actual value is paired with a corresponding prediction. If their sizes do not match, later calculations could fail or give meaningless results. This simple check helps prevent runtime errors and protects the reliability of our metric computations. To evaluate the model, we first compute raw errors by subtracting each predicted value from the corresponding actual value. This gives a set of differences that show how far each prediction is from the true energy consumption. These errors are important because they are the foundation for summary measures such as the mean error and the mean absolute error, which describe the model's overall performance. To find the mean error, we take the average of all the differences between the actual and predicted values using a mean function. We then convert this average to a standard numeric format, such as a floating point number. This mean error shows the overall bias of the model's predictions, indicating whether it tends to overestimate or underestimate the true values on average. To compute the mean absolute error, we start with the array of differences between the actual and predicted values. We then use a numerical tool to take the absolute value of each difference so they are all positive. Next, we calculate the average of these absolute values, which gives the typical size of the prediction error in kilowatt hours. Finally, we convert this average to a standard floating point number for use in later calculations or reporting. To find the root mean squared error, we first compute the mean squared error by taking each prediction error, squaring it to give more weight to larger mistakes, and then averaging these squared values. We then convert this result to a floating point number for precision. This metric tells us the typical size of the errors, with larger errors contributing more strongly to the final value. Root mean squared error is found by taking the square root of the mean squared error. This step converts the error back into the original units of the data, which makes the result easier to interpret. Using this measure also highlights larger prediction errors, giving a more intuitive sense of how well the model is performing. To create a simple baseline for comparison, we first compute the average of the actual energy consumption values. This average is then used as a naive prediction for every data point. It provides a straightforward benchmark that helps us judge how much better our model performs. We use a numerical computing tool to calculate this mean efficiently on the full dataset. We build a simple baseline model by creating an array of predictions that has the same length as the array of actual values. Using a numerical tool, we fill this new array with a single constant value, which is the mean of the actual values. This means the baseline predicts the same average consumption for every entry. We then use this constant prediction as a reference point to compare how much better or worse more complex models perform. To find the total squared error for the naive baseline, we subtract each baseline prediction from the actual value and square this difference to highlight larger mistakes. We then add up all these squared differences to obtain the total squared error. Finally, we represent this total as a floating point number to maintain numerical precision. The code computes the total squared error of the model's predictions. It first finds the error for each data point by subtracting the predicted value from the actual value. Each error is then squared to give more weight to larger mistakes. These squared errors are added together to produce the total squared error, which is finally converted to a floating point number for precise representation. This calculation produces the improvement ratio, which shows how much error the model removes compared to a simple baseline. It first divides the model's sum of squared errors by the baseline's sum of squared errors to find the proportion of error that still remains. Then it subtracts this value from 1 to get the fraction of the baseline error that the model has eliminated. A higher improvement ratio means the model has reduced more of the original error. The script ends by printing a brief summary of the regression metrics. It reports the mean error bias, which shows the average direction and size of the prediction errors, followed by the mean absolute error, which gives the average size of the errors regardless of direction. It then shows the root mean squared error, which emphasizes larger errors, and finally the improvement ratio, which compares the model's performance to a simple baseline that always predicts the mean of the actual values. Together, these metrics provide a quick overview of how well the model is performing. This script evaluates how well a regression model predicts energy consumption using a small dataset. It computes the mean error to show prediction bias, the mean absolute error to capture the average size of the errors, and the root mean squared error to emphasize larger mistakes. The script also compares the model to a simple baseline that always predicts the average of the actual values and calculates an improvement ratio to show how much better the model is than this naive approach. When you run it, you see these metrics printed, giving a concise summary of the model's accuracy and its improvement over the baseline. Comparing model performance. After you understand regression metrics on small examples, the next step is to compare different models on the same prediction task. To do this fairly, both models must be evaluated on exactly the same data. For instance, if two models predict monthly electricity usage for the same 10 households, and you compute their mean absolute and mean squared errors, you can directly compare their performance. If Model A has a mean absolute error of 5 kilowatt-hours and Model B has 8, then Model A's predictions are, on average, 3 kilowatt-hours closer to the true values, so it is performing better on this task. When comparing models, you should look at several metrics because each reveals different aspects of performance. For example, If one model has a lower mean absolute error but a higher root mean squared error than another, it may be making a few very large mistakes. This means it can seem better on average while still producing some highly inaccurate predictions, which could be risky in practice. The other model with a lower root mean squared error may be more consistent and have fewer extreme errors. Thinking this way helps you understand what the metrics really mean for real-world use, even with a small dataset. When you evaluate models, use small numeric examples to compare accuracy with practical considerations. For instance, if two models predict daily blood glucose and one has a slightly lower mean absolute error but is much more complex, ask whether that small gain matters in a clinical setting. You may find that both models are safe enough and that the more accurate one only helps when readings are already stable. This mindset helps you focus on how differences in error actually affect real-world outcomes, whether you are measuring energy use, time, or medical values. Interpreting error scale. Error units explained. When you evaluate regression metrics, always pay attention to the units of the error because they tie the numbers back to the real-world quantity you are predicting. If you predict house prices in dollars, an average error of 10,000 means your predictions are off by about $10,000. And if you predict weight in kilograms, an average error of 3 means you are typically off by 3 kilograms. This connection between the metric and the measurement scale makes the results meaningful and helps you avoid misinterpreting them. Common metrics like mean absolute error and root mean squared error share the same units as the target variable, which makes them easier to interpret intuitively. When explaining model performance to non-technical stakeholders, describe errors in the same units as the outcome so the results feel concrete and relatable. For example, it is clearer to say that sales forecasts are off by a few units per store per day, or that travel time predictions are off by a few minutes, than to rely on abstract statistical metrics. Expressing performance this way helps people quickly judge whether the model is accurate enough for their real-world needs and supports better, more informed decisions about using the model. When evaluating regression models, it is important to know which metrics keep the original units of the target variable, because this affects how we interpret them. Mean absolute error and root mean squared error stay in the same units as the target, so they can be read as typical deviations such as an average error of 0.5 degree Celsius. In contrast, mean squared error is expressed in squared units, which is less intuitive. For clear real-world communication in areas like finance, healthcare, or engineering, practitioners usually prefer metrics that return to the original scale. Relative versus absolute error. When evaluating regression models, it is important to distinguish between absolute and relative error. Absolute error is the direct difference between the predicted and actual values, measured in the original units, such as dollars. However, this alone does not show how large the mistake is compared with the size of the true value. Relative error addresses this by scaling the absolute error by the true value and expressing it as a percentage, which reveals the error's proportional impact. Relative error is important when predicted values differ greatly in size or when we compare results across different situations. The same absolute error can be minor in one case, but severe in another, depending on the overall scale. For example, a $10,000 error on a $300,000 house is a small percentage, but the same error on a $20,000 car is a very large percentage. By focusing on percentage rather than fixed amounts, relative error provides a fair way to judge accuracy, especially in areas like finance or retail, where scale matters. When evaluating regression models, you should look at both absolute and relative errors to understand performance. Absolute error matters most when small deviations are critical, such as in medical settings. Relative error is more useful when the importance of an error depends on the scale, like in sales forecasts. Always interpret errors in real-world units and as a proportion of the true values, so the model is both statistically sound and practically useful for decisions. Error acceptability context. When evaluating regression metrics, you must judge errors not only by their size, but by whether they are acceptable in the real-world context. What counts as acceptable depends on the stakes, the domain, and the decisions based on the model's predictions. A $10 error in coffee shop sales might not matter, but a very small error in medication dosage could be critical. The same numerical error can therefore be harmless in one setting and unacceptable in another. So metrics must always be interpreted in terms of their real-world impact on people, resources, or safety. To judge whether an error is acceptable, you must compare it to relevant limits such as regulations or business tolerances. The same size error can be fine in one setting, but serious in another. For example, being off by 3 minutes when predicting bus arrivals might be acceptable in a city with unpredictable traffic. But that level of error would not be acceptable for aircraft landing schedules, which require precise coordination. In manufacturing, prediction errors in part dimensions are acceptable as long as they stay within engineering tolerances. Overall, what matters is how much deviation is tolerable in that specific context. When judging whether a model's errors are acceptable, you need to balance accuracy against cost and speed. A very accurate model may require complex features and expensive data, while a simpler model with slightly larger errors can be cheaper and easier to maintain. Different applications tolerate different error levels, such as allowing more error in fast triage or long-term forecasts, but demanding higher precision for detailed treatment planning or next-day inventory. In the end, the key question is whether the error level fits the domain's risk tolerance and operational constraints. In this lecture, you learned to describe common regression metrics in intuitive terms, compute simple regression metrics on small numeric examples, and interpret regression metric values in the context of the original problem scale. In the next lecture, Lecture B, we will go over classification metrics.
Thank you for your attention. See you all in the next lecture.